this session, I am going to talk about or going to demonstrate that how FDF file can be generated for different types of systems and how simulation run using SIESTA. And I also explain some post-processing tools. So I send you a FDF data file. It's basically a template. So I go to the NMM. Let me see. I create a directory test and in which I am going to do some calculations. So it's basically let me rename it. It's a template file. And if I try to look at it, so it is FDF data. It's for gold. So let us make it for silicon because we have generated the pseudo potential of silicon. So it is system name is silicon. System level I also mentioned it as silicon. Number of species means how many atoms are there in silicon. There are 2 atoms. Number of species will be 1 because only silicon atom is there, but the number of atoms will be 2. And what is the atomic number of silicon? 14. Sure. Okay. So it's a 14 and it is silicon. These are the changes which I made here, and these are the coordinates of this. I am using fractional coordinates, and fractional coordinates will be there. Anyone tell me what is the lattice constant of this silicon? .25 because 2 number of atoms should be there in this LC. Can anyone tell me that what is the lattice constant of silicon? Silicon lattice constant. Lattice constant of silicon. .43, right? 5.43. Let us take it like this. 5.43 is its lattice constant. So in place of this, I am using 5.43. And what are the lattice vectors? The lattice vectors of FCC, because it's a FCC diamond like structure, so it is 0.5, 0.5, and here it is 0.5. It's a diamond like structure, right? It is a diamond like structure. So these are the lattice vectors of this. So now let me explain this information which I mentioned here, that why I am using 0, 0, 0, 0 and 0.25, 0.25 and 0.25 here. So let us have a look at it, that why I am using it. So 5.43 is the lattice constant. So for FCC, so it is a diamond like structure for silicon. And what do you mean by diamond like structure? So before moving towards a diamond, first of all let me talk about that what is a FCC lattice, right? So all of us are familiar with the FCC structure. So FCC structure is like this. This is FCC structure, means this is one atom, this is another atom, means an atom is sitting at the corner, every corner, and another atom is sitting in the face, means it is the center of this face, center of this face, center of this face, and center of this face also, and center of this face and the center of this face. So this is our FCC lattice. So I made changes in a file in which information of gold is contained, and gold is basically FCC lattice. And as we know that FCC lattice contained 4 atoms per unit cell, but in that FDF we have mentioned only 0, 0, 0. That means these are the primitive coordinates. These are the primitive coordinates which I am using. So what is the meaning of it? Primitive means minimum number of atoms should be there in your input file or in your structure. So how is that minimum? Let me, and the lattice vectors which I mentioned, these are the 0.5, 0.5. These are the lattice vectors which I mentioned, 0.5, 0.5, 0.5, 0, sorry, I'm a little bit wrong. 0.5, sorry, 0.0, 0.5, 0.5, 0.5, 0.0, 0.5. So these are the lattice vector of FCC. What does it mean? That means what I will do to draw these lattice vectors corresponding to the primitive cell, I will join the nearest neighbors. So nearest neighbor of this will be, this is one, this is another, and this is the third one. So I joined these. So I have 10 vectors. So using these vectors, I can complete a it was like this. So this blue colored cell which I have shown here, so this is green colored cell is the FCC, and this blue colored is the primitive cell to this one. And if I try to look at it, what it is sitting in one plane, and it is sitting in the another plane, and it is in the third plane. So one may be the XY plane, say this is X, this is Y, and say this is Z axis. So if I keep in mind this one, then which plane is this one? This is the XY plane. So an atom sitting here, its coordinates are this one, and another is the this is Z will be this one, X will be this Y. So it is the YZ plane. YZ plane has these coordinates. This is the vector, and for ZX it will be this one. It is the Z and it is the X. So these are the coordinates for this, right? So that means these are the primitive vectors. So now from FCC, I will switch over from here to the diamond-like structure. So what is a diamond-like structure? If I look at the definition of it, then in FCC, if I draw a body diagonal, then this is the body diagonal, and I penetrate another FCC lattice along the body diagonal up to the 1/4. So 1/4 means I will draw here again a FCC lattice, right? It was like this. This is another FCC lattice. So in the primitive cell, one atom is sitting here because one atom is contributing in the primitive mode for FCC lattice. Similarly, another FCC lattice which I immersed along the body diagonal up to the 1/4, then its coordinates will be again 0.25, 0.25 and 0.25. So that means the atoms, one atom is sitting here and another atom is sitting at 0.25, 0.25 and 0.25. So that's what I did in the FDF file. You have to feel the structure, that what is happening. This is one FCC and this is another FCC. So, keeping this in mind, I have written these as a lattice vectors for FCC. These are the coordinates for this. Fractional means I have to express the coordinates in 0 and 1, not actual coordinates. But if you want to find out the actual coordinates, then you have to multiply these with the corresponding what we call lattice constant. Then actual coordinates will be determined. Let us now try to visualize this. So for visualization, I simply copied this. I simply copied this information and let us make a directory SI, and inside SI I opened another file, say test.fdf. Just to understand, .fdf is the extension of this file. So it is the FDF file. It contains only structural information, nothing else. I just saved it, and then what I will do, there is a package known as GDIS, sudo apt-get install GDIS. It's a part of Ubuntu, so you directly download it. So please try to install GDIS. You installed GDIS? Have you installed? Narendra will help you. There is some. Narendra is there? Narendra, Ananya, Shivani, अराउंड लो जरा जहां दिक्कत आ रही है प्लीज. GDIS, right? So what I did, अब कमांड दूंगा मैं GDIS, it is test.fdf. ये देखिए ये ओपन हो जाएगा. There is some GDIS. There is some problem. There is some problem with GDIS. Yeah, test.fdf. Number of pattern species. Just structural information. Let me check it again. System name is there. Oh, sorry. There is some error. Actually, it should be 1, not 2. This one indicates species. So, one species is what? This is the species number. So, we are having silicon. So, that's why it gives some error. So, it should be 1 here. If 2 different types of species are there, then you have to change it. See, this is the structure of silicon. It's a diamond-like structure. You can rotate it and feel it. It's a diamond-like structure of silicon. I have made changes in FDF data, so I copied FDF data from here to the silicon directory, test directory. With the name of si.fdf. Let me check it, visi.fdf. Oh, I have not changed it. So I just saved it. Yeah, it is for this. I just made changes to it. In place of this, it is 1. Now let me talk about its other parameters. Any name, si.fdf. Better if you save it with the si.fdf or any, means which is suitable. si.fdf. I renamed it with the name si.fdf. So it is visi.fdf. So this is the structural information. Then this is the basis set which you have to use. DZP is the best choice. DZP is the best choice. Otherwise, there are different choices are available. One choice is SZ, SZP, DZ, DZP. Another choices are DZDP, TZ, TZP, TZDP. These are the different choices. But as these choices are there, computational will go very high. So better you use DZP. And this is the PAO energy shift. Better if you use this value as 0.20 MeV. It is MeV, milli electron volt. Don't make it capital M. Capital M will become mega. So PA energy should be 20 milli electron volt to 50 milli electron volt. In this range, it gives a better result. For this, you have to see the convergence tests. I am not going about to talk about those here, but I mentioned these in my lectures on YouTube. And here it is the exchange correlation author. Pseudopotential we have generated is the CA. So we have to go to the SIESTA manual that what is the flag for the CA, exchange correlation function. And let us see whether CA is LDA or GGA, right? whether it is LDA or GGA, you have. So let me go to the home, and then it is the folder. And inside SIESTA there is a file named this docs. So to compile it, you must have LaTeX or Kyle. So I have Kyle installed, otherwise you will get its manual online also, but I have Kyle already, so I compiled it, and it will make a FDF for me. Sorry, not FDF but PDF. So it's a PDF will be generated. Yeah, it's there with us. So exchange correlation functionals at the 48 number page, right? See, CA means LDA. XC functional means LDA is there and it is a CA, and it is represented by CA only. And then exchange correlation functional, it was mentioned LD or LSD, then PW92, it is LDA, and for this is GGA. And you can use for sodium or simple metals LDA if you use, but if you use GGA, that will also be better. But for rest of the calculations you have to use particularly GGA. So that means if I want to use another pseudopotential with GGA flavor, then what will you do? You must need a pseudopotential which is GGA, right? So let us do one thing. Means we will make a pseudopotential for PBE. So for that, what will you do in the silicon folder? Let us make a slide change for that. For PBE. So for PBE, CD, yeah, NMM, SIESTA, pseudo atom tutorial SI underscore test, PS generation SI underscore test, right? Then you have to remove this directory. I am again going into the same directory. Remove -r. Once you give a command with the rm space -r and the file name, then it can never be recovered. So if you want to delete something on command line, be sure if something is deleted on command line, either in the Windows or the DOS prompt or on the terminal, there is very least probability that those files can be recovered. So बड़ा सोच समझ के remove command का use करना है आप लोगों को. So I am just deleting it. I just delete it. Then I make changes into the si.inp. It is CAR. In place of CAR, what will you use? You use PBR. It is the PB is the flag for the GGA exchange correlation functional in the atom code, where R is the relativistic. Then I save it, again run it, sh // utils pg.sh and si.inp. Now I will copy this pseudopotential from here. I copied this pseudopotential si.psf you can copy it manually. So I copied it from here to the home. I am using direct command. Home, in home there is a directory nmm 2023, inside it is tests, not tests, it's not there. Oh, in the desktop. I am doing this on the desktop. Test directory I have created on the desktop. Oh, PSF, this, and desktop nmm, it is tests, and inside it there is a this one. So I copied this from there to there. So on command line I just copied it. See, this, it's not there. Okay, it is copied in the inside the silicon. I just copied it here. Then I bring this si.fdf from here, because it is in the previous directory, to this working directory. Now two files are there. One file is this one and another file is this one. These two files are required, and test file I created just to visualize it on the GDIS. Any structure you can visualize on the GDIS. So we require these two files only, FDF file and PSF file, right? So let me now explain again FDF file again. si.fdf. Anyone please share the script to run it. अनन्या, स्क्रिप्ट है? स्क्रिप्ट शेयर कर दो, मेरे को पेन ड्राइव में डाल के दे दो, है ना? So what do we do? Okay, I am just telling that what is the information. So I told these parameters. So these parameters I set by testing these parameters, by doing some energy convergence tests. So this is one thing, and you have to change this XC author, because I am using PBE functional. GGA, PBE functional, spin polarized. You can play with the spin. So you can, if you want to do magnetic calculation, you have to make it true. If you don't want to do magnetic calculations, don't want to include the spin, then it is a non-magnetic calculation. Right? I mentioned everything. SCF iteration 2000 is sufficient. 20 MeV. No. 20 MeV to 50 MeV. And DM mixing bait. So it tells us the mixing parameter, that how much mixing will be there, because in the previous step and next step these some parameters will be mixing, means density matrix, it's relating to the density matrix. So the previous step and the next step. Then number pulley, it's a type of forces, then need not to worry. And for by default SIESTA will do calculation for if DMINAT spin is false, then it is ferromagnetic case, and if it is true, then it is anti-ferromagnetic by default. But it will optimize the spin automatically. So you can see the spin also, but I will talk about that later on. You can play with this tolerance parameter. So it is a default value, means 10 raised to power minus 4, it's the meaning of it, this parameter. Better you should take it minus 5. And if you want to do phonon calculations, then you can use it as minus 6 also sometimes. depending upon, but it will take more time to converge, and sometimes things will not converge. Script WhatsApp पे भी share की है, you can download that script also. And mesh cutoff. Better if you take 300 or 350 Rydberg mesh cutoff. If you take smaller mesh cutoff, then results may vary. But 300 or 350 gives you a better result, and convergence will also be little bit faster. But if you take smaller values, convergence will be fast, but results are not reliable. If you take larger values, then sometimes it will take a lot of time to converge. So better if you prefer to use 300 or 350 Rydberg. And these values are chosen by using energy convergence test, means when energy leads to one value. I have mentioned all these things in the YouTube lectures also. This is smearing temperature, and this is K grid Moncost pack. It is the K sampling, right? So for actual calculations, better if you take it is 1515 band structure calculation. It tells us about the integration in the reciprocal space. It's not a room temperature. This is not a room temperature. This is smearing temperature. It helps to converge the these values, converge your calculation. Sometimes you have to increase it. You can increase it also. It helps in some systems. Things will converge, then there is no problem. If some issues are there, then you can play with the DM mixing rate or this temperature. This is not a room temperature where all the calculations can be done at the 0 Kelvin. जितनी भी calculations 0 Kelvin पे हो रही हैं. अगर आपने किसी temperature पे calculations करनी है, then you have to do molecular dynamics. Then you have to use certain thermostats. So I am using this as a K grid, means it helps in the integration in the reciprocal space. I will talk about it later on. It's a very tricky issue, because when you have to move from 3D to 2D, 3D to 2D or 1D or 0D, then this mesh will change. Then this is another. If you take these values, then your density of state will be better. If you take smaller mesh, then density of states will not give you the reliable results. Especially these two parameters, 0.05 and 4000. Then CG step will be 0. If you want to relax the structure, cell, and if you want to relax some molecule, then it should be 1000 or more than that. If you want to relax the cell, say you are sitting in a room and you need to optimize the height, length, breadth and height of this room for a particular number of persons. For that you have to change it. So for that CG step should be 0. But if you want to move these atoms, means the persons who are sitting, they have to rearrange themselves. जैसे पहले दिन आप लोग आए थे तो अपने हिसाब से बैठ के थे, उसके बाद आपने अपनी पोजीशंस को रीअरेंज किया. That's what atoms will do. Atoms know where to go and how to go. किसके साथ बैठना और कहाँ बैठना है एटम्स को पता है. जब हाइड्रोजन को ऑक्सीजन मिलेगा फेवरेबल कंडीशन में तो पानी बनेगा, वाटर इज देयर. कार्बन को उस पर्टिकुलर कंडीशन में अपने आप डायमंड भी बना देगा, ग्रेफाइट भी बना देगा अकॉर्डिंग टू दोज कंडीशंस। हम उसको फोर्स नहीं कर रहे हैं। So similar situation is there. अगर आपने एटम्स को रीअरेंज करना है, मूव करना है, तो सीजी स्टेप 1000 आएंगे। बट अगर आपने सिर्फ सेल को रिलैक्स करना है तो सीजी स्टेप 0 आएगा। तो सबसे पहले हम सेल को रिलैक्स करते हैं। सो ये ब्रीफ इंट्रोडक्शन मैंने आप लोगों को एफडीएफ फाइल की थी। आई थिंक नरेंद्र हैज आल्सो मेंशन्ड इट इन द मॉर्निंग सेशन। नाउ व्हाट डू वी डू? There is script given by Ananya to me. So let us see where is that script. You have also copied it. ebsled.sh. This was the script, and I just put this script here. Yeah, it's there. This is the script. So let me now discuss with you this script. BISI. Even you can do all these things manually. It is a shell script. Say lattice constant is what? Lattice constant is, what is the value of the lattice constant? 5.43. So let us start with the 5. Say it is 5. मैं crude calculation बता रहा हूँ. You have to start with the say 4.5. In a step of 0.1 up to 6.0 or say 15.0. I am running a simulation from 4.5 to 15.0 in a step of 0.1. It was also given you. Then LC in FDF data. So my file is si.fdf. si.fdf. Let us make it as SI $I. I means the values of I taken from here 4.5 to 15.0 in a step of 0.1, and then SIESTA will run, because the command for SIESTA will be this, simply SIESTA, right? And it is SI means I will use this file here as an input, and out file will be written like this. SI dot $I means I will update automatically, and then out, right? And what is LC? Because what I need to change the lattice constant manually so that optimized value will be obtained. So for that LC is the variable. So you have to make changes in the FDF. So regarding that, so what I will do, I will make changes here. It is LC will be there. Yeah, lattice constant. You have to make changes in place of this because it will automatically change it. So it is LC, right? It's a variable. Now I defined. I saved it and then run the script. So to run the script, change the mode of this script, because script should be in the executable mode. So you have to change its mode by using a command chmod plus x and the name of the file whose permissions you want to change. Let us do one thing first of all. ls-al ls-al. Say this file is not this file is not executable, but when I give a command chmod plus x EBS Now if I try to see it, now it will become a executable. 5x is written there. This is a way to make it executable. Now I am not running SIESTA directly, but I am running SIESTA with the help of a script. So I just run this script evslet.sh. This is the command. That's it. Oh, there is some problem. Species level doesn't exist. Let us see where is the problem. si.fdf species level. System name is this one, number of species, number of atoms, chemical species level. It is taking it. Oh, sorry. I have to save this cbslet.sh. Sorry. si.fdf. Oh, I have to save it. I have to save it because I have not saved it. Now I have saved it. ls./evs. Now it's running. So it will take some time. So I am running it in the parallel mode. I am running it in the parallel mode because on my system it is installed in parallel mode, so that it will be completed more quickly. So I am deactivating Conda. And SIESTA underscore parallel, this is it is my SIESTA in parallel mode. I have installed separately, so I am using this. Sorry, it is vi evslet.sh. I think it is to run it in the parallel mode. You have not installed it yet. I have installed. So for it, mpi run dash number of processes 8 SIESTA underscore bar. So now I will run it. So /evs. Now it was running in the parallel mode. And let me check it. See, these are the resources which it was using. 8 processors are used simultaneously. Just a minute. I think I have done this for today. Now I will talk to you. I come to your desks and then talk to you. That's all for today.